In this section, we're going to look at linear equations. In this video, we're going to try to get a handle on what makes a relationship linear. So let's look at two situations that on the face of it may not seem to be related. Let's say that an hourly worker earns $17 per hour. So we're going to let X be the hours worked and Y be the money earned. And now let's go a little ways down the page and look at something completely dissimilar to that, or seemingly dissimilar to that. You bulk order basil, the spice, at $4.49 per ounce. And we can let X be the number of ounces you order, and Y be the money spent. So these two examples don't have a lot to do with one another. They both involve money, but here it's money earned, here it's money spent, and the X values mean totally different things. But what these two situations do have in common is a constant rate of change. So what do I mean by that? Well, suppose that you will work 0 hours. Then, of course, you earn $0. You work 1 hour. You earn $17. You work 2 hours. You earn $34. So when you go from 0 to 1 hour, that gives you $17. When you go from 1 hour to 2 hours, that gives you an additional $17. If you go now from 2 hours to 3 hours, well, that's going to be another $17 for 51 in total. So every additional hour That's you an additional $17. And this spice example is very similar in that regard. If you don't order anything, of course, you spend $0 on it. If you order 1 ounce, you spend $4.49 on it. If you order 2 ounces, that's $8.98. So when we went from 0 to 1, the cost increased by $4.49. When we went from 1 to 2, the cost increased by $4.49. And we're about out of space, but if you went from 2 ounces to 3, the cost would increase by $4.49 for a total of $13.47. So every time X goes up by 1, Y goes up by some fixed amount. This is a linear relationship. And linear relationships are special. Most relationships are not linear. For example, an object is dropped off a bridge. And we'll let X be the number of seconds since the object was dropped. And we'll let Y be the distance the object has fallen after X seconds. And this time I'm going to go ahead and give you an equation. The distance an object falls after X seconds is 4.9x squared. Our units here are meters. And this is if you neglect air resistance. So let's look what happens to Y as X changes. At time 0, the object hasn't started falling yet. So it's fallen a distance of 0 meters. After 1 second, the object has fallen 4.9 meters. So the distance has increased by 4.9. After 2 seconds, the object has fallen 4.9 times 4 meters. Let me just type that into my calculator. It's fallen 19.6 meters. So when you go from 1 second to 2 seconds, the distance the object has fallen has increased by 14.7 meters. So you see, we don't have a constant rate of change here. Over 1 second, the object's distance increased by 4.9 meters. After another second, it increased by a different amount, 14.7 meters. And this, if you think about the physics of the situation, makes sense. Falling objects accelerate. The object is moving faster here than it was here. It makes sense that it covers more distance. But the takeaway message from our point of view is that this relationship is not a linear relationship. Unlike the previous examples where we had constant rates of change, we have nothing like that here. So what makes a relationship linear? Well, that will be our next thing to ask ourselves.